Alright, silly people, here's the situation. We're going to have a bunch of questions about gamma functions, or a computational equivalent of the gamma functions. So that's given by this integral here. Famously can't be really done analytically, but we can computationally do it, and we're going to be doing a lot of that. So first of all, we have to write a program to make a graph of the integrand itself, just from 0 to 5 for different curves, a equals 2, 3, and 4. And so that should be easy enough. We're just going to go down here and define the integrand as f of x, and it actually is going to be a function of a and x. And I just realized that I should probably import numpy and matplotlib pyplot as plt, just because we're going to be doing some plots and stuff. And then it's going to return x raised to the a minus 1 times numpy exp just minus x. Yeah, minus x. And then we can create an input list for to go into the function, which is going to be the linspace from 0 to 5 with 1,000 steps, and just plot a bunch of those XLS versus the function with calling specific values of a. It wants 2, 3, and 4. So I'm going to do 2 XLS. I'm going to label each one as we go. Label will be equal to just a equals whichever one we're on. And so I'm just going to take this plot line here and copy it down a couple of times. Change this to a 4 and this to a 3. There's this to a 3 and this to a 4. And we should have, after I add the legend, a decent plot of the integrands for different values of a, right? So those are cool. The next bit is to show analytically that the maximum falls off at x equals a minus 1. You can already observe this here. For the a equals 4, the maximum happens at x equals 3, so 4 minus 1. And then this is 3 minus 1, and this is 2 minus 1. So that is observable, but we can also show it analytically if we just take our integrand, which is x to the a minus 1 times e to the minus x. If we take the derivative of this with respect to x, I'm showing all the LaTeX of this video, it's going to be awesome. Yeah, you take the derivative of that and set it equal to 0, you'll find your maximum. So that derivative via the product rule is just a minus 1 times x to the a minus 2 e to the minus x minus minus x raised to the a minus 1 times e to the minus x, and you still have 0 on the right hand side, right? So cancel out the e to the minus x things, cancel out various powers of x. You can very quickly solve that for x, and you'll get a minus 1, which shows that the maximums, yeah, they happen at x equals a minus 1, so that's awesome. Next bit, it says that we're going to be using this transformational variables where we do z equals x over c plus x. The thing is that you want z equals 1/2 to be the middle of the peak, so you want z equals 1/2 to be at the middle of each of these, which means you're going to be plugging in a minus 1 for x in this sort of variable transformation. So it was x, so a minus 1 over c plus x, so also a minus 1 down here. And you're supposed to be solving for c to get the left-hand side to look like 1/2. That's this. So that's a easy solve. Just do a couple of algebra steps to solve for c equals a minus 1. It's actually pretty sensible. So whenever you go into actually doing the integral numerically, we can affect that change. Part D, before we can calculate the gamma function, there is another detail we need to attend to. Yeah, it's just about how the integrand itself can be weird at large numbers and small numbers, and so you can instead write x to the a minus 1 as e to the a minus 1 times natural log of x, which is true. And the utility of this is that we can put it all into one exponent function. So right now we have power law times an exponent. Instead, we're going to have a exponent of the power, which is a minus 1, times the np dot log of x. And instead of multiplying another exponent to it, we'll just move the power of that exponent inside this exponent by writing minus x. And you can see that it gives you the exact same plots, so you know it's something that works, and it is pretty good at dealing with the singularities and stuff. So now we can actually go about writing the gamma function, and I'm going to do that in a different code cell. So I'm going to take this and bring it down below our analytic stuff down here and define gamma of a, and then the integration method is left to the reader to figure out. I'm going to use Gaussian quadrature because it's what I've used in like the last 6 videos, so I'm pretty used to it now. N equals 100 points for Gaussian quadrature. A equals, or actually, so when I was first trying this code, I was just writing out the shell of Gaussian quadrature a lot, and then redefining a within the gamma function, which is not good. Just know that the lower bound of the integral is 0, and the formulas that I write down to do the integral will reflect that. So the Gaussian quadrature starts with doing x comma w equals Gauss xw of n. Again, this is using the version of the Gaussian quadrature code that Newman wrote. It's in the online resources. And then it's not wx, it's xw. But yeah, plus 0.5 times b minus a, except a is 0 for all of these, so I'm going to just backspace these. A, when I'm talking about it right now, being the lower bound of the integral, not, you know, the gamma function that we're trying to calculate. This is times w. And then you do s equals 0.0 4k in range n. And inside this for loop is where we're going to make our like transformation of variables happen. So if you go back a little bit into the book and you look at the part where it talks about how to do this variable transformation, it doesn't really say how to do the integrand, how to change that. So I'm just going to show you how. With the transformation of variables, c equals x over c plus x, we're going to, that is equivalent to saying, if you solve for x, that x equals z times c in a fraction. So zc over 1 minus z, right? It's not what I thought of, like originally, but that's what it is after deriving it. And so if you take the derivative of this to get the Jacobian for this, you will get that dz is equal to, you actually get that dx is equal to c over 1 minus z squared dz. And so if you're doing an integral from 0 to infinity of f of x dx, given this variable transformation, you're instead doing the integral from 0 to 1, and it's going to be multiplied by c over 1 minus z squared, and then you're going to plug into your integrand just z over, let me write it in a fraction actually, but it is just c over 1 minus z is what it should be, right? So with that in mind, and that's also, let me write dz at the end of that. So that's cool. That's only going to show up in this line though. So we're going to take this line here and say c times f of z times c divided by 1 minus z, and then and that's, the function is actually 2 arguments, it's a and x. We'll just put a here, and then we'll divide it all by 1 minus z squared. So let me put this in another set of parentheses here. The computer doesn't know what z and c are yet. C is, of course, as we found earlier, going to be a minus 1. And z is what we're going to index via the Gaussian quadrature. Z is just xp indexed k. And to complete the line, we have to multiply it by the weights of the Gaussian quadrature. And with that, I think this should work. Let me multiply that and not multiply this. Okay, I think that should work. After that, you can return s and have it print. We're going to check gamma of 3/2, which is a known result. So give that a run, and it doesn't like it. B is not defined. Oh yeah, I need to say that the upper bound of the integral is 1. My bad. I need to get 0.886. So that's commensurate with what the book is saying. So we did it all good. We can also check if we calculate the gamma functions of 3, 6, and 10. We'll get to 120 and 362,880. We can just do that real quick by running a for n in 2, 6, and 10, and just printing gamma of n. That should work pretty well. Wait. Oh yeah, it should be 3, 6, and 10, not 2, 6, and 10. My bad, that was a little scary. But yeah, I think it all works. All right.